Okay, welcome back. So the last 2 weeks we focused on finite groups, and recall that finite groups are the mathematical structure that underlies discrete symmetries in a system. So here is a simple example that I gave before. If I look at a discrete system where the degrees of freedom are like the position of this piece of Duplo, then I can ask about symmetries that leave the shape of this piece of Duplo invariant, and clearly these are the rotations by pi over 2 around the symmetry axis. So this means that the symmetry group of the shape of this object is a group of order 4, so it's an abstract group that has a certain composition structure that encodes the way that the symmetries of this piece of Duplo compose with each other. And then we've looked at representations of such groups, and the representations, so which take like every element in the group and assign a linear transformation to it on your system. So in this case, the linear transformations are just the linear transformations that do the rotations by pi over 2. They actually implement the symmetry on your system. Okay, and we've classified more or less the irreducible representations of finite groups. So we know to a certain extent how discrete symmetries can be implemented in physical systems. Now certainly this is a useful thing to know, and you've got a crash course on this in the past 2 weeks. It will appear in various places in your physics education. But especially for particle physics, and also other areas of theoretical physics, it is actually the infinite groups, more precisely the continuous groups, that play a even more important role. So just to start the discussion of continuous groups, I've looked around for some attributes in my attic that have continuous symmetries. So here is a simple example. It's just a half bowl. And clearly this also has rotational symmetries, but a lot more than the piece of Duplo that I showed before. At least if I ignore the colors on this half bowl, then I can see I can rotate it by any real angle alpha, and it will leave the shape invariant. So that means that the symmetry group of this half bowl is actually infinite, but it's also continuous in the sense that I can parameterize the rotations by a continuous parameter, which is the angle of the rotation around its symmetry axis. Now one can have even larger symmetry groups that are not described by a single continuous parameter, but by a family of them. And if I take a full bowl, then I can rotate around every axis. So there is, in this case, there are 3 angles that I have to specify to specify a symmetry transformation of this bowl. Okay, so to understand these infinite symmetry groups that are parameterized by continuous parameters, we have to look at Lie groups. And this will really be the topic of the remainder of this lecture course. What is the mathematical structure that comes with this additional continuous structure that I have on the symmetries? Okay, so let's get started. So the prime example of a continuous symmetry group is that of the 2D rotations, as I just showed you for this half bowl. And it's clear that 2D rotations are parameterized by a single real parameter, which I can write to be alpha, which is just the angle by which I rotate the system. So if I choose some coordinate system, I can rotate the coordinate system by some angle alpha. And clearly, if I compose 2 two-dimensional rotations by angle alpha, then just the angles sum up. So this means that the underlying group is really that of a circle. So this is my group, and if you like, I can explicitly write down some algebraic definition of the group. I could say that it's the given by the set, which is just the real numbers from 0 up to 2 pi, with the binary operation of the group just being addition modulo say 2 pi. Right? So this is just the abstract group, and the way that the symmetry kind of arises in terms of my physical object is via representation. That associates to every group element. So let's denote the general group element by G as function of this real parameter alpha. It has to associate to this a linear transformation of some vector space. So suppose we look at R2 now. So it associates a 2 by 2 matrix, and this matrix that is associated to the rotation by angle alpha is probably well known to you. So it's given by this 2 by 2 matrix, cosine alpha, sine alpha, minus sine alpha, cosine alpha, which is exactly the matrix that transforms this basis to the rotated basis by angle alpha. Okay, so we have an explicit group here and an explicit representation on R2. So these are examples of a Lie group and its representation. So let me give you a formal definition of this. So definition, a Lie group G is a group whose underlying set, say G, has an additional structure, has the additional structure of an n-dimensional manifold. Okay, so this is a Lie group, say, of dimension n. Okay, so it's an n-dimensional manifold. So here's a cartoon of a two-dimensional manifold. So we can think of every point in this smooth surface being an element of a group. So we would have at least one point here that is the identity of the group. And we have these other points. And we know, because this is a group, that every pair of points has to combine via the binary operation of the group into a third point. So this means that I get various mappings from my my manifold to the manifold itself. Now what we have to do is we have to require that this manifold structure is actually compatible with the group structure. So such that the group operations, so this means if I take some pair of elements on my manifold and I look at their binary relation, or if I take some element in the group and I look at its image under the inverse, that these have to be smooth mappings, such that the group operations are smooth mappings. So this is a definition of the Lie group. Now perhaps it's good just to recall you what it means to have the structure of an n-dimensional manifold. So this is really saying that in the vicinity of any element of the set G, we can parameterize uniquely the elements by n real parameters. So this means, so if I'm looking in the vicinity of, say, this element G, then I really can parameterize these elements by some subset in the n-dimensional real space. Okay. So this is a Lie group. We also have the notion of a representation, and this just goes through as we had introduced them in the first lecture. The only additional requirement we have to make is that the matrix that we assign to a group element actually depends in a differentiable way on the parameters of your group elements. So note a representation of a Lie group. So that's a mapping from G to say the capital N by N matrices, complex matrices, then we really want these matrices to depend smoothly on the group element. The representation is required to be smooth. Okay? And this is certainly the case in this example, because the trigonometric functions, they are smooth functions of alpha. So what we want to do now is we want to study what happens in the close vicinity of the identity element of the group. And in order to do so, we're going to choose a parameterization. So let's choose a parameterization. So G is function of some parameters alpha. So alpha here are really n-component real vectors. So we choose a parameterization in the vicinity of the identity element of the group, such that if I set these parameters alpha equal to 0, that I get the identity element. Okay, and what we're going to do is we're going to look at a representation of this group, G, expanded around the identity element. Because if I now look, at the matrix associated to an element G of alpha that is close to the identity, and since I'm requiring the representation to be smooth, I can perform a Taylor expansion on this matrix. So I can approximate it by the value of the representation at the identity element, so alpha equal to 0. But this is the identity element, so any representation of the identity element should be the identity matrix. So this is going to be the n-dimensional identity matrix. And then the first order correction is going to depend on the derivative here. So I get a correction term which is alpha A times the derivative with respect to alpha A of dg alpha evaluated at alpha equal to 0. Right, and then in general I get higher order terms, so the first one being of order alpha squared, or the components of alpha squared. Okay? So for each, so here I'm using summation convention, right? So I'm summing over A. So here A is summing from 1 up to n. Because this is an n-dimensional manifold, I have n real parameters that parameterize this neighborhood. And for each of these n choices of parameter, I get here a matrix. And this matrix I denote by x sub A, and it's called the generator. So I get 1 for every A from 1 to n. These are the generators of our Lie group G. In this particular representation D. So of G in representation D. Okay, so let's just have a look what this means pictorially. So, I mean, suppose that I look at the trajectories of the group elements in this group when I only put like one of these real parameters equal to non-zero or non-zero and increasing. So that would give me some trajectory. So suppose this is the trajectory when I increase alpha 1. So in this picture I'm drawing a two-dimensional manifold, so there will be two real parameters, alpha 1 and alpha 2, corresponding to different trajectories in this group. Then what I'm doing is I'm taking the derivative of this group element, or more precisely the matrix that I assign to this group element at the origin. So here is the identity. We know that this is the identity matrix, so here really you should think of this picture as the set of matrices that I've assigned to my continuous group G. So then these generators, they really correspond to the tangent vectors to these curves. So I have a tangent vector here, x2, and another tangent vector x1. And together, these two generators, what they do is they span the tangent space at the identity element. So the generators span the tangent space to the group, or actually the matrices that I associate to the group at the identity. Okay, so let's just have a quick look at what this means for the 2D rotation group. So I have an explicit expression here for the matrices associated to the group element of parameter alpha. So since there is just one parameter, I just get one generator. So for 2D rotations, so 2D rotational group, if you like, which is called SO2 because these matrices, they are orthogonal matrices of determinant 1. So the generator is X. So taking the derivative here and then setting alpha equal to 0, I simply get 0, minus 1, 1, 0. Okay. So given some Lie group together with a representation, in this way I can determine the generators that span the tangent space of this group. Now what we'd like to do is to take some arbitrary tangent vector and then turn it back into a group element. So let me explain you how to do this. Maybe I can reuse this figure. Okay. So we would like to reconstruct group elements from the generators. But note that if we take an element of this form, the identity matrix plus some linear combination of the generators, that for this to be a group element, what we really need is that alpha of A is infinitesimal. Only if alpha A is infinitesimal. Because only when it's infinitesimal we can really neglect the alpha squared term. So what can we do to start with some finite non-infinitesimal tangent vector, so a finite linear combination of the generators, to build some actual group element in the group. So a natural thing to do is to decompose your generator into many small generators. Right, so this is my generator alpha A XA. If first I can look at a much shorter generator, say alpha A XA, maybe over K, where K is very large, then certainly this element is going to be very small, close to infinitesimal when I take K to be very large. So there will be a element in the group that is very close to this generator when I add the identity matrix. Maybe I should write here the representation of the group. Right, so what we're going to do is we're going to decompose alpha A XA as a sum of K identical terms which we can naturally associate to group elements. So we want to associate each of these terms to the group element is the identity plus alpha A over K XA. And then essentially add them all up again in the group. But okay, we cannot add things in the group because this typically a group is a curved object. But what we can do is, because the group has a binary operation, is we can compose these group elements. So suppose I take two of these tiny generators, which correspond to a group element close to the identity. I can take their composition, and that will give a group element that is slightly further from the identity. What I then can do is I can compose it again with a tiny one of this, so it will be slightly further again. And if I do that k times, then I'll end up at some group element that is, so I want to associate to this, the group element that is really the kth power of this group element that is very close to the identity. Okay? Now, certainly, I mean, the result here, so this group element, is going to depend on k. But if I take k to be very large, then it will converge to some fixed group element. So what happens when I take k to be very large here? So if I take the limit of k to infinity of alpha a over k x a to the power k. So recall, I mean, this is a matrix, right? So these are not just numbers, but matrices. But we can still use the, say, the binomial formula to decompose this and write this as an alternative sum. M is 0 to infinity, where we collect all mth powers of x. And if you check, what you get as a combinatorial factor is 1 over m factorial times, alpha a x a to the power m. But this is, I mean, if you forget that these are matrices, this is just the expansion of the exponential. So let's just say that this defines for me the exponential of a matrix, alpha a x a. And now, since we're taking products of elements that are genuine group elements, this is going to be a genuine group element itself. So we found a mapping, which is really the exponential mapping from generators to group elements. So that's quite nice. We know how to go from group elements to generators by just expanding around the identity. And then given any generator, we can go back to a group element that is not necessarily close to the identity by taking this exponential of a matrix. So here's a fun fact that will be quite useful. So fact. If G, so if you like the set or the manifold underlying your group, is connected and compact. So what does that mean? Okay, connected, I'm sure you can have some idea what it means. So here is an example of a manifold which is not connected. So it's really saying that, I mean, starting from the identity element of the group, I can reach every element of the group by some continuous path. So what does compact mean? So compact means that, well, okay, I'm not going to give the full mathematical definition, but all the Lie groups that we will encounter in this course will actually be built from matrices. And as soon as they're built from matrices, compact just means that if I look at the matrix elements I, j, that they can only vary within some finite range. So in particular, if I take the, say, the absolute value, it will be bounded by some constant, some universal constant. Okay? And really in this course we're going to focus on connected and compact groups. So this fact will hold for any group that we'll be interested in. Okay? Then any group element can be written as the exponential of some generator. So then any group element G and G can be obtained as, okay, dg is the exponential of some generator for some real parameters alpha. Okay? So note also that here the manifold structure becomes very clear, because not only do I know that in every neighborhood of some group element I can find some parameters that parameterize this neighborhood, but actually I can use these coefficients of the generators to parameterize the full manifold. So this is really a strong statement. Okay, let me just say that there will be an exercise which is to check that if I take the exponential of the generator of SO2, that is exactly of the form that we saw in the beginning. So if I start with the generator of SO2, then taking the exponential, I get my previous formula back.